If you had gone to the site of St. Paul's Cathedral in London shortly before 1665, you would not have found the grand and soaring structure one finds there now. Instead, you would have found a shabby and dilapidated building, falling down due to the neglect of a government only recently re-established after years of revolution and civil war. Before that, following the break with the Roman Catholic Church, Henry VIII had sold off various properties and ornaments of the building to raise funds for wars and other projects that suited his objectives. In 1661, lightning had struck the central spire of the church, rendering the building more or less unusable for any sort of worship, either Catholic or Protestant. Nevertheless, had you gone on the right day between 1661 and 1666, you might have found one or more of a new group of citizens working on its grounds. These men were a part of a rising group of intellectuals and scholars brought to London by the endowed Gresham professorships to probe the secrets of nature and teach all men what wonders they and others were uncovering. Among this group were two men of some note who would reshape London both figuratively and literally in the years to come. One man you might have encountered would have been Christopher Wren, once the Gresham Professor of Astronomy, now the Salviati Professor of Astronomy at Oxford. He had been tasked with the rebuilding of the cathedral by the government of Charles II, and as part of that work, he was often found at the site, taking measurements and making sketches for what would be an architectural masterpiece. Another might have been the polymath and Gresham Professor of Geometry, one Robert Hooke. Wren's close friend and one-time classmate at All Souls College, Oxford, Hooke had spent a great deal of time in the dilapidated structure, where the great heights, especially in the damaged spire, afforded him the opportunity to undertake a number of experiments with pendula and barometers to better understand both motion and the Earth's atmosphere. Both men were members of the fledgling gathering of scholars in London known as the Royal Society, and were under the tutelage of that group's most august personage, the Reverend Robert Boyle, whose work with air pumps and vacuums was becoming known around Europe. The work in and on St. Paul's would come to a sudden and catastrophic stop on September 2nd, 1666, when most of the city of London inside the old Roman walls, along with portions to the west outside the gates, burned to the ground, leaving St. Paul's in absolute ruin. This conflagration would in time give rise to a new London, and a new St. Paul's that would be an architectural masterpiece that would be copied by many an architect afterward. As the new St. Paul's rose from the ruins of the old, so too would a new understanding of the motions of the celestial bodies that would put to rest the questions and objections of the scholastic philosophers once and for all. It would be the very men who had worked in the ruins of the old cathedral who would set the stage for the new edifice that would be constructed in a rural university some 50 miles away by a reclusive mathematician known to few before 1678. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 26, Setting the Stage. When you read the typical discussion of the scientific revolution that is centered on the transition from a geocentric cosmology to a heliocentric one, the usual thing you find is that after the work of Kepler and Galileo is discussed, there is a jump directly to Isaac Newton and the Principia. Traditionally said to have been born in the same year that Galileo died, Newton takes on a sort of biblical significance as a scientific Elisha to Galileo's Elijah, kind of receiving a double portion of a philosophical spirit that allows him to create his breathtakingly complete reimagining of physics, space, and time. While this story is a good one, especially if you're British, it neglects about 50 years of work by any number of important scientists on a broad number of fields. And herein lies the difficulty that leads to storytellers simplifying this whole thing. In all of the complexity that one finds in looking at this period of 50 years, what do you choose to talk about? What figures and ideas do you choose to emphasize? There's amazing work being done in astronomy, biology, anatomy and medicine, chemistry, mathematics, cartography, geology, and oceanography, in addition to various fundamental advances in physics that we've already mentioned in previous episodes. In addition, and we haven't even talked about this even a little bit, to stunning advances in engineering. So how do you pick and pull a narrative out of all of that? Whose work gets emphasized and whose work doesn't? Whose work gets examined and whose work doesn't? Whose contributions are highlighted while others are left for a later time and a different thread of the tapestry? In our metaphor, which currents do we follow and thus what shores do we visit? Which ports of call do we bypass in order to make progress on our ultimate destination, at least in this voyage? My guide for this episode, one that is necessarily transitional in nature, is the title of our series, Finding Our Place. I'm going to focus on those individuals whose work helps us build the bridge from Galileo to Newton specifically. This means we'll more or less neglect the work of figures such as Sir Francis Bacon and Robert Boyle in England, Giovanni Domenico Cassini, first in Italy and then later France, and the Polish astronomer Johannes Hevelius. Each of these figures make truly important and valuable contributions either to developing the practice of science, as in the case of Bacon and Boyle, or in the work of astronomy with Cassini and Hevelius. Rather, we're going to look for this episode at those figures who pick up the baton carried by Galileo and deliver it to the place where the young Lucasian professor of mathematics in sleepy Cambridge will bring together the various threads and understandings of the motions of the objects in the heavens and those on the earth to create a synthesis that can be said to spark both the Industrial Revolution and the Enlightenment. The first two figures we have to look at are a pair of Jesuit-educated and trained figures, Rene Descartes and Giovanni Battista Riccioli. Riccioli was a Jesuit priest who thought of himself more as a theologian than as a natural philosopher, but who, through his interest in astronomy, took up the investigation of many of Galileo's claims regarding motion. While I will leave his biographical details to a supplemental episode, let's take a few minutes to look at what is generally considered his greatest and most influential work, Almagestum Novum, or, in English, The New Almagest. Published in 10 volumes in 1651, the work considered both Galileo's contributions and work on falling bodies, as well as his evidence for supporting a heliocentric system. In the case of the motion of earthbound objects, Riccioli set out to test Galileo's law of falling bodies in two parts. First, he wanted to determine if Galileo's claims of a specific mathematical relationship regarding accelerated motion was true. Second, he wanted to assess Galileo's claims regarding whether objects of different masses or different densities fell at the same rates. To test these claims, Riccioli proceeded to conduct tests from very large heights in strictly controlled conditions. Before we discuss the results of these tests, it should be noted that in the very fact that such care and rigor was exercised in the investigation of falling objects clearly shows that Galileo's new method of doing natural philosophy, by gathering verifiable evidence through what we would now call experimentation, had gained an authority that did not exist before his work at the beginning of the 17th century. In this, we can see the beginning of the end of natural philosophy as a credible philosophical pursuit. Henceforth, as we've already discussed in our Puy de Dôme episode, its authority will pass to the establishment of facts based on observational evidence, and it is those things that will actually carry authority henceforth. For Riccioli, citing the ideas of Aristotle or Plato was no longer a sufficient argument to establish the truth of an explanation of something in the physical world. So let's look at those two parts. In the first case, Riccioli confirmed Galileo's law of fall, and in doing so made the first reliable measurement of the acceleration of a dense, compact falling object near the surface of the Earth. While Galileo's work is usually cited as the thing that undoes Aristotle's explanation of terrestrial motion, I think it is the work done by Riccioli that really eviscerated the 2,000-year-old understanding of motion. While it didn't establish the idea of inertia, we'll get to that a little later, it did open space for new ideas to be considered. When Riccioli confirmed the law of falling bodies, he, in essence, told the scholarly world that Aristotle really is fundamentally wrong about his description of terrestrial motion, and thus all other ideas, from the work of the 13th and 14th century scholastic philosophers to the most contemporary thinkers like Galileo, must be reconsidered and reevaluated anew. Everything's kind of open game again. In the second case, Riccioli shows that while Galileo's experiments had been accurate for small distances, they neglected the effect of the air through which a dropped object would have to move. As the height from which an object was dropped was increased, the Jesuit priests found that those objects that were the same mass but more dense, and thus they were smaller, would hit the ground earlier than larger, less dense objects. In other words, if you dropped a 1 kilogram ball of wood and a 1 kilogram ball of iron from the same height, the iron ball would take less time to reach the ground, something established by one of the earliest uses of multiple trials of the same experiment to establish the repeatability of a phenomenon. Riccioli attributes this distance to the effect of what we would now call air resistance or drag, something that increased as the size and speed of the following object increased. In doing this, Riccioli was able to explain the reasons for Aristotle's erroneous descriptions of motion, thus removing another obstacle to the acceptance of this new understanding of falling objects and motion in general. It is useful here to note that much of this was done using a pendulum as a timing device. Riccioli had extended Galileo's work on pendula, showing that for small oscillations, the period of the oscillation was independent of the amplitude of the oscillation. In other words, if you're working with a 2-meter-long pendulum, the time it took for the string to swing back and forth once was the same whether you pulled the heavy mass at the end of the string 5 centimeters to the side or 10 centimeters to the side. He also established that this relationship did not hold in cases where the pendulum was initially displaced a large angle from its straight up and down orientation. Something around 40 degrees is what he actually tested. What I think's really cool about all of this is in doing these tests, he used the only truly regular motion he knew of, that of the night sky. He would count the number of swings that would occur for 2 stars to cross the meridian in the southern sky on successive days. He was able to use this to create a pendulum that would swing exactly once per second, or what he actually did is have it swing 86,400 times in one day, something that he actually tested on 2 different occasions. Once he had done this, he was able to create pendula that would oscillate once per some longer time interval, say, once per 10 seconds, or once per minute, or once per hour, by comparing them to this 1-second pendulum. It will be Christiaan Huygens, who we'll talk about down the road here in just a bit, who will build on this work and the earlier work of Galileo to create the first long-running pendulum clocks. As such, it is important to recognize that these clocks tie back to a measurement system calibrated directly to the motion of the heavens, specifically that celestial sphere we talked about so many episodes ago. While we now keep time by counting the number of wavelengths of a particular frequency of light emitted by a certain electron transition in a cesium atom, and boy, that's a lot to say, there was a time not so long ago that our way of measuring the passage of the present from the past to the future was based on the motions of the night sky. So much has this changed that in my astronomy classes, I now teach what I call a nighttime sky activity on how to use the Big Dipper and its handle to mark the passage of time. something that never fails to amaze my students as they recognize for the first time that the motions of the stars when one faces north turn counterclockwise, a bit like a backwards clock face. The other significant area of discussion Riccioli engaged in as part of the Almagestum Novum was an assessment of the various models of the solar system. In this, author Michael Flynn puts forth the idea that Riccioli's book was actually much more along the lines of what Pope Urban VIII had wanted Galileo to write. Professor Christopher Graney of Jefferson Community and Technical College writes that much of the book consisted of a careful presentation and evaluation of the arguments for and against Copernicanism. Graney points out that these arguments, 49 for heliocentrism and 77 against it, are presented as a legitimate scientific debate, with experimental evidence put forth when available and considered fairly. Unlike other attacks on the work of Galileo, there are few arguments made from religious or theological grounds, and those that are advanced carry little weight in the discussion. Now it should be noted that Riccioli is not comparing Copernicus with Ptolemy, as Galileo did, as he and nearly every other astronomer by 1651 understood that Galileo's telescopic observations of the phases of Venus had demolished the Ptolemaic model. Rather, his comparison is between the geoheliocentric picture and that of Copernicus. While Riccioli's preference was for a somewhat different arrangement of that geoheliocentric model than the one that Tycho had used, the arguments he considered applied to each fairly similarly. In Riccioli's evaluation, he comes down on the geoheliocentric side, but not for some scripturally based reason, but instead because he felt that it best fit the available scientific evidence at the time. So what was that evidence? There were really three pieces of evidence that carried the most weight. The first had to do with falling bodies. If the Earth rotated on its axis, then a ball carried to the top of a tall tower, especially if that tower is at the equator, would be moving faster than a ball that was laying on the ground at the base of the tower. The way to think of this is that over the course of one day, the ball with greater altitude would have to trace out a circle with a slightly bigger circumference than the one on the ground in the same amount of time. That means it had a greater speed. If that ball at the top of the tower was released and it maintained its inertia all the way down, the way a ball dropped from the top of the mast of a moving ship would, then it should be observed to land not at the base of the tower, but just a little bit to the east of it. The taller the tower, the greater this effect would have been. Riccioli, in his experiments with falling bodies that we discussed just a bit earlier, never observed this phenomenon. His second objection had to do with the idea that if one fired an artillery shell due north, the cannon from which the shell was fired, and thus the shell itself, would be traveling a little bit faster than that point to the north, and so the shell again should deflect to the east in its travel. This effect, however, would not be found for a shell fired due east or west, as all of those points on a due or east or west line would be traveling at the same speed. Again, this was not observed in artillery fire from a real cannon used in warfare. Finally, his third objection was when one looked at stars through a telescope, the stars perfect points of light, but instead small disks. This, Riccioli argued, meant that the physical sizes of the stars in the Copernican system would have to be larger than the entire solar system, while in the geoheliocentric model, they would be less far away and thus much smaller. As it turns out, there is an explanation for each of these negative results. In the first case, there was no tower tall enough to demonstrate the results in the presence of the atmosphere that would yield that sort of a measurable deflection that Riccioli had been looking for. This effect, however, has subsequently been observed. In the second case, we now call what Riccioli was talking about the Coriolis effect, and it can be best observed in the deflection of the Earth's atmosphere to create counterclockwise flow of air around the center of a low-pressure system. The third issue had to do with what we now call the diffraction of light waves entering an aperture, such as the objective lens of a telescope. This phenomenon would not be completely unraveled until the 19th century, when George Bedell Airy would show how such disks could form from images of point-like light sources, such as stars. With the exception of the Coriolis effect, which might have been ferreted out from a comprehensive mapping of trade winds, none of these lines of evidence were available to Riccioli. As such, he reached his conclusion on what he felt to be the best available evidence. The question wasn't one where the evidence made a slam-dunk case for one model or the other. Rather, there was seemingly conflicting evidence that had to be weighed or, in Galileo's term, assayed. The question was how much relative weight to give each argument. 14 years later, just as Newton was beginning to think about these very same issues, Riccioli published another notable work, the Astronomia Riformata. In this, he reported a number of observational advances in astronomy and perhaps most notably refined his version of the geo-heliocentric model to take into account Kepler's elliptical orbits, as it was becoming clear by that point that this orbital shape was by far superior in predicting planetary positions to any model using exclusively circular motions for the planets. It is of some note for our story that it was an attack by a lesser-known astronomer on this work that engaged the interest of the Royal Society in England and drew Isaac Newton out of seclusion to discuss the motion of both falling bodies and projectiles, something that will become extremely important to our story down the line a couple of episodes. The next figure we need to discuss is a man so influential in the field of philosophy that I don't think it would be much of a stretch to say that he was the greatest and most broadly relevant thinker of the early modern age. In fact, I might say that he's the most important Western thinker after only Aristotle himself. Rene Descartes' major contributions include developing a whole new branch of mathematics, re-establishing the philosophical idea of mind-body dualism, developing an alternative model of the atom that would inform both chemistry and physics for centuries, and developing a mechanistic view of physics and the universe that would have profound influence on natural philosophers and thinkers for hundreds of years. While our focus will be on this last aspect of his work, let me make a few comments on a few of the other bits. His work in mathematics was to develop the foundations of what is known as analytic geometry. With my sincere apologies to the mathematicians in the audience, who will likely groan and roll their eyes at this oversimplification, what Descartes does in developing analytic geometry is combine or bridge the two branches of mathematics known as geometry with its subdiscipline of trigonometry and algebra. The key to this work was the ability to represent geometry and geometrical figures within a space defined by a coordinate system based on right angles known as a Cartesian coordinate system. In 2 dimensions, this is simply the xy coordinates one would see on a piece of standard graph paper. As strange as it may seem, prior to Descartes' mathematical work, this did not exist as a mathematical idea. That every point in space could be thought of as being represented by a unique x and y component, or in 3 dimensions, x, y, and z components, was completely new. This allowed Descartes to represent every idea in Euclidean geometry as an algebraic relationship in a rectilinear coordinate system defined by those right angles. For example, whereas in geometry a circle is defined as all points in a plane equidistant from a single point, in analytic geometry, the circle could now be expressed as all pairs of xy coordinates that satisfied the algebraic relationship x squared plus y squared equals r squared. The geometry of triangles, known as trigonometry, becomes the set of ratios in the xy coordinates of these points on a circle. If I may be allowed to riff for just a moment here, what Descartes does in this is redefine how human beings think of space in the grandest of terms. Prior to his mathematical work, human beings tended to think of space in geometric terms. In the minds of men like Copernicus and Rheticus, Kepler and Galileo, space is exclusively defined by geometric figures such as spheres, ellipses, and arches. The grandest of buildings were built on the curves and ratios found in nature. Think of the great cathedrals and basilicas of Europe built before the 1600s. And then contrast this with our modern definition of space as depicted in art and architecture. Nowadays, we have imposed on space the Cartesian grid of lines crossing each other at right angles. I'd be willing to bet that for those of you who go to work or school in a large institutional structure, if you look up, you'll see Descartes' XY coordinate system in the ceiling of the room you're in. If you have tiled floors, as we do in the building I teach in, you'll see it there as well. You'll see that XY coordinate system, Descartes' coordinate system, has come to fundamentally symbolize the rationalization of both space and our modern compartmentalization of work life. When we walk into an office building filled with right angles and well-defined grids, we are not moved to artistic expression or spiritual epiphany. We are instead guided to think rationally and logically. It is when we enter those spaces that reject the Cartesian forms that we are more easily transported to the state of being where we let go of the rational experience to something that transcends such descriptions. When we walk into a cathedral or a music hall whose space is inspired by the organic and geometric forms of nature, our minds seem to naturally shift into a different mode of experience. Even the most analytic of us are called to a more aesthetic, or dare I say, spiritual state of mind that goes beyond what one expects to think or feel in the Cartesian boxes where we spend so much of our time. The same is true when we move out of our aggressively gridded urban spaces to re-encounter and re-engage with the natural world. Even in the simple act of laying out and looking up into the darkening night sky with its seemingly spherical geometry, calls us to ask bigger and deeper questions, just as our ancestors did so many millennia ago. But enough of our digression. Let's return to Descartes' contributions to understanding the structure of the universe. We discussed Descartes' version of atomism in our episode called The Corpuscular Atom, but it is useful now to place that discussion in the broader context of his mechanical or mechanistic picture of the cosmos. Like Galileo, Descartes rejected the Aristotelian description of objects as having a base matter and a set of causes that resulted in the object's properties. Instead, as was always the case in atomism, the properties of the object rose from the nature of the matter itself. It came from the properties of the atoms. For Descartes, atoms were not point-like masses moving through a void, but rather extended things, sort of vortices in a plenum or fluid-like things that makes up the universe and defines its space. In this picture, all motion takes place as the interaction between these swirling vortices at a tiny level. On the level of things we see, this results in the expansion of an idea first put forward by Galileo, though in an incorrect form, that idea of inertia. What Galileo had said was that if an object was at rest, it would remain so until a force was applied to that object, at which point it would speed up or accelerate. If that force was then removed, the object would, in the absence of friction or air resistance, as might be the case for an object moving along the surface of a frozen lake, and by the way, that is the specific example Galileo uses, the object might continue to travel along the surface of the lake without slowing down. Galileo reasoned that if one could imagine the entire surface of the Earth covered with ice, then the object would travel in a circle around the Earth without changing its speed, exactly like objects traveling along circular paths in the heavens do. Hence, Galileo would develop a law of inertia that said once an object was moving, its natural motion was to travel in a circle at constant speed or constant velocity. In effect, Galileo was bringing the motions of the objects in the heavens down to the Earth. Descartes, on the other hand, recognizing the action of gravitation, though he didn't have a good handle on exactly how to characterize it, was able to express the law of inertia in its more correct form by saying that the natural motion of an object once moving would be to travel in a straight line at constant speed. The only reason, he said, that Galileo's object would curve around into a circle was due to the influence of the Earth. In this, Descartes may have well been influenced by both William Gilbert's thoughts on magnetism and Kepler's work on the motion of celestial objects requiring a force that gets weaker further from the sun. While Descartes vehemently rejected Gilbert's action at a distance description of magnetism, something that he instead accounted for through his interaction of his corpuscular vortex atoms, he did recognize that objects could apply forces to other objects through space using that mechanism. What's interesting, however, is that Descartes' idea of force was something different from what would eventually emerge from the work of Newton, as can be seen in his attempt to explain circular motion through the idea of a center fleeing property possessed by a body traveling along in a circular trajectory. It would be left to the work of Huygens and Hooke to rectify this error. Before we leave Descartes' physics of motion, we should also note that his third law of motion concerned the interaction of two bodies in a collision. In it, he develops a relationship that attempts to predict the motion of two bodies after they collide. In this relationship, he claims that it is the size and speed of an object that is important, thus anticipating, to a degree, Newton's fundamentally important idea of momentum and rejecting the Aristotelian idea of impetus. The final idea of Descartes we should talk about before moving on is his cosmology. It is clear from his work titled The World that Descartes is a Copernican and was ready to publish his ideas on the universe based on that model. However, with the condemnation of Copernicanism and the conviction of Galileo on charges of heresy in 1633, Descartes withdrew the publication of the work, and only later put out the ideas he had about celestial motion in works where the motions of the objects in the heavens, most notably the earth here, were treated in ways that did not contravene the Church's injunction, while still allowing for a Copernican interpretation. What is important in these works is that he puts forward the idea of a mechanistic universe wherein motion is not something that has to be impelled by God. Instead, it is a mechanical system that once set in motion will continue to operate without further intervention through the interaction of the vortices that both define and fill space. It is the successive collisions of his corpuscles, the vortex atoms, that would create and sustain motion, and so the model of Descartes would rest on an advanced theory of collisions. This model was profoundly intuitive in its explanation of the forces that drove both terrestrial and celestial motion, and thus held ascendancy over the ideas of Newton for quite some time, especially on the European continent, as his ideas didn't require some sort of occult action at a distance force like gravitation to account for planetary motions. Interestingly, this mechanical or mechanistic philosophy would set in motion the rise of deism and the reaction against it that would occupy so many conversations, philosophical and otherwise, over the course of the next 2 centuries. The next figure we want to spend just a bit of time talking about is Christiaan Huygens. Huygens was a Dutch scientist born in 1629, and he worked in a vast array of fields including probability theory, microscopy, horology, or the study and measurement of time, astronomy, and physics, to name just a few. He was, without question, one of those European polymaths who corresponded with everyone about everything and was respected in all the circles as one of the best minds in almost every field of inquiry and study. For this episode, though, we want to focus in on just a couple of things. We've already mentioned the first of these, and that would be his work in taking pendulums and making them the heart of precision timekeeping devices, something he achieved in 1656. Huygens chronometers truly set the standard in accurate timekeeping and became essential in much of the astronomical research that would follow their development. It's hard to imagine Flamsteed's groundbreaking and breathtaking work at the Royal Observatory without Huygens timepieces. As part of this work, he was the first to establish the relationship describing the period of the swing of a simple pendulum as a function of the square root of its length, and as something independent of the mass of the pendulum bob, at least for small oscillations. In addition to this, he would begin the rigorous development of coil spring timepieces that would eventually lead to the solution of the longitude problem some 100 years later. This work was essentially similar to work being done simultaneously by another figure we'll discuss, Robert Hooke. Both men would create designs for chronometers based on their research, though recent research seems to suggest that Hooke may have had many of the ideas specific to the implementation prior to Huygens. Another idea in which Huygens, working with his brother Constantine, made important discoveries was in astronomy, where he discovered the true nature of the rings of Saturn, Saturn's largest moon Titan, and he observed the nebular regions in the belt and sword of the constellation of Orion for the first time. These discoveries were made due to the significantly larger telescopes the Huygens brothers were able to produce due to advanced glass making and grinding technologies that had been developed during this time that astronomers were just beginning to take advantage of. In the field of physics, Huygens was a strong follower of Descartes' mechanical philosophy early in his life, though this support would wane in later years as he studied the work of Newton. While never completely rejecting Descartes' ideas, he understood the difficulties in explaining motion the contact collision-based ideas created that were more easily resolved by Newton's action at a distance gravitational force, something we'll look at in greater detail a couple of episodes from now. He also did enormously important work in optics, including developing an explanation of the various macroscopic properties of geometric optics, such as the laws of reflection and refraction, based on a wave description of light. In this description, the speed of light is both finite and changeable depending on the medium through which it is traveling, and thus it acts much as water waves do when they encounter barriers or obstacles. In the thread we're following in this series, though, Huygens' greatest contribution was his work on understanding circular motion. He was able to show that for objects that travel in circles, say a ball being swung in a horizontal plane by being attached to a string, the force on the ball has to be directed inwards, and it has to follow a very specific mathematical expression that involves the speed of the object moving in a circle and the distance the object is from the center of the circle. If you've ever ridden on a children's merry-go-round at the park, you're probably familiar with this. And by the way, if you haven't done this or can't remember the experience, consider this podcast episode as your permission to go out and play on one. If anyone asks, you can tell them you're conducting experiments to better understand the physics of orbiting objects, and that Dr. Davies said you could do that, or whatever works. Or, if you have kids, you can take them along and use that as your cover story. Anyways, if you imagine holding on to the metal U-shaped bar at the end of the spinning horizontal disc that is the merry-go-round itself, you know that your arms have to pull towards the center of the disc to keep from traveling off the disc on a straight line that's tangent to the disc, i.e. flying off the merry-go-round when you let go. That's, the vernacular way of saying all the physics words. Now note, if you let go, you do not travel directly away from the center of the disc as you might think if you were being acted on by some sort of centrifugal or center-pushing force. Now, if the merry-go-round spins faster, you have to pull harder to hang on, and the magnitude of the pull increases pretty rapidly the faster you go, indicating that the relationship between how fast the disc is spinning and how much force your arms have to exert is more than just proportional to the speed at which you're traveling. Huygens was the first person to put all of this together in 1659, in order to show that whatever the force on a planet is, it has to be able to point towards the center of the orbit, i.e. the sun. This idea would be picked up by and expanded on by the final figure we'll discuss in this episode, Robert Hooke. Before we leave Huygens, however, we should note that his other important work in physics was to simplify the mechanics of collisions first put forward by Descartes. In both his work on circular motion and in collision theory, he will provide an essential bridge from the ideas of Descartes to those of Isaac Newton. Now, as we turn to Hooke, it should be noted that Hooke may be the singularly most unappreciated figure in all of science. It's hard to document all of his accomplishments, from his work in physics, to his attempts to measure stellar parallax, to serving on the committee that rebuilt London after the Great Fire of 1666, to doing for the microscope what Galileo did for the telescope. He was, in all of the important ways, save one, the true embodiment of the Renaissance man. And that one area, at least as near as I can tell, was his personality. There will be a point where we delve into this in greater detail, but suffice it to say that Robert Hooke was not the easiest man in the world to get along with. In addition to being creative, ingenious, brilliant, and persistent, he was vain, contentious, jealous, and more than just a bit dishonest from time to time, especially later in his life. All of this would conspire to have him leave a tremendous legacy that Isaac Newton, the man with whom Hooke most famously clashed, would spend a great deal of time and energy working to hide and obscure for posterity. We'll leave Hooke's work in microscopy for a later series on the history of medicine. That the book he produced in 1665, titled The Micrographia, was perhaps the most influential book of the period between Galileo's Starry Messenger and Newton's Principia, and it coincides with that period marked by the formation of scientific societies. Very much in the vein of a modern coffee table book, the drawings and diagrams it contained of things observed through the newly popular instrument amazed the intelligentsia of Europe in the same way that Galileo's Starry Messenger had some 50 years earlier. In physics, Hooke's work parallels Huygens in many ways, though it is clear that the two men worked essentially independently of each other. One area where Hooke made significant contributions was in understanding elasticity, or the way in which things stretch when a force is applied to them. In this, he developed the first force law in demonstrating that when an object is stretched, it will exert a restoring force that is proportional to the amount it has been stretched from its equilibrium configuration. This can be demonstrated with the simple rubber band. If you take a rubber band and stretch it, say 5 centimeters, it will pull back on your stretching finger with a given force. If you double the amount you stretch the spring, the force will also double. This is now known as Hooke's law, and has been shown to be true for objects that are compressed, such as springs or stone columns as well. The other area of interest to us is Hooke's work on gravitation. By observing what are known as circular pendula, Hooke came to the same conclusions that Huygens had. A circular pendulum is an easy thing to imagine. Think of a mass, say a ball, hung from a single point by a string. The ball is then allowed to swing in a circular path rather than in just 2 dimensions around that point so that the string makes a constant angle with the vertical. What Hooke recognizes from this study of stretching objects is that the string will stretch a bit when the mass is hung from it, and so the force it exerts on the mass will point from the mass back to the suspension point along the string. Thus, when the mass is traveling in a circular path with the string always at an angle, some of that force along the string will also point back towards the center of the circle. Now, if you're finding this a bit hard to create a mental picture of, and that's pretty understandable if you are, we'll post a diagram out on our website, thescientificodyssey.typepad.com, for you to get a better idea of what's going on here. From this, what Hooke observes is that while it is possible to produce a circular path if one is very, very careful when initially starting the circular pendulum, what is much more likely to happen is that the path of the pendulum bob will be somewhat elliptical, and that the long axis of that ellipse will rotate or precess around the center of the figure. This, he realized, was in line with Kepler's description of planetary orbits and observations of the moon's actual path around the Earth. This recognition prompted him to write in the Philosophical Transactions of the Royal Society in 1666, quote, "I will explain a system of the world very different from any yet received. It is founded on the following positions. 1. That all the heavenly bodies have not only a gravitation of their parts to their proper center, but that they also mutually attract each other within their spheres of action. 2. That all bodies having a simple motion will continue to move in a straight line unless continuously deflected from it by some extraneous force, causing them to describe a circle, an ellipse, or some other curve. 3. That this attraction is so much the greater as the bodies are nearer. As to the portion in which those forces diminish by an increase of distance, I own that I have not discovered it." End quote. As we will see, these conclusions form the foundation of Newton's own gravitational theory. Unfortunately for Hooke, he was never able to ferret out that mathematical expression for his gravitational force, and thus he's unable to apply his suppositions in a rigorous way to any known systems. As such, his description cannot be said to have any sort of inverse square dependence that will be so important in Newton's work, nor was it thought by Hooke to be something that necessarily acted universally, i.e., between all objects regardless of their status as either celestial or terrestrial objects. As we will see, this commonly shared work will become a source of great conflict between Newton and Hooke. Regardless of this, however, it is clear from the work of Huygens and Hooke that the minds of the late Renaissance thinkers were converging on an explanation of the observations of the motions of the celestial bodies that might resolve the one question that occupied the thoughts of so many. Did the earth move? As we wrap up this episode, I again want to say thanks to everyone who's joined the crew of the Odyssey. To the old sea dogs who have been on our many voyages, it's great to have your experience, and to those who have recently signed up or maybe been impressed into service, welcome aboard. If there's anything you'd like to have me talk about that relates to the topics that we've been covering, things like Renaissance astronomy, the scientific revolution, the rise of scientific societies, etc., let me know, either by sending me a note at cldavies@mac.com, hitting me up at Twitter @ChadDavies, or by posting something to the podcast's Facebook page. As I said earlier in this episode, there are a lot of things I'm sort of glossing over, and so if you have something you'd really like to know more about, let me know, and I'll see what I can do. If you haven't already done so, may I encourage you to subscribe to the show on whatever service you're listening to us on? It helps us move up in the various podcast rankings, which means more people see that we exist, when that means, of course, we have more people joining the crew. Another way for you to do this is to leave us a review. While I'm not able to see all the reviews from all sorts of the places across the globe, I would like to thank those who left the lovely reviews on the US version of iTunes. Wow! You guys were just super generous in your praise. Finally, if you know of people you think might enjoy the show, why not send them an email with a link to the show and a brief description? As everyone knows, the best way to advertise something is through word of mouth. So if you know someone at work or school or wherever with whom you end up talking science or history with, go ahead and tell them about the show and invite them to give it a try. We're always accepting more crew members, and in this case I really do believe the more the merrier. Let's keep building this really fantastic community that's coming together. Finally, I once again want to say thanks to the Blue Dot Sessions for letting us use their music as a backdrop for the show. I think the atmospheric compositions of theirs we use is great for all sorts of things, and I'll tell you, I use it as something to occupy that part of my brain that always wants to get distracted by stuff when I'm researching or writing the podcast. While we use the work that they do that fits what we're doing here, they have a variety of different moods and genres that they explore, and I would encourage everyone to go out to their website, www.sessions.blue, to check it out. They've recently added 5 new compositions to their wonderful album Aeronaut, and I've been really enjoying their recent foray into jazz on the Tiny Tiny Trio release. Check it out. Next time, we're going to take a bit of a detour and look at the astronomical work of the Jesuit order during and after the Galileo affair from the Isle of Wight to the far-off shores of China. So until then, full sails on your journey.